And you'll have to, can you bend it so it gets to point up there?
Yes.
I'm gonna like
You'll have to kind of move it
Okay.
to both. Yeah, it's not easy. Page 148 we're on. You have to read 5.5 and 5.6 tonight. That's what we're going over right now. Let's talk a little about the surface of the Earth. And you're going to keep this in mind as we're studying other planets and bodies. The surface of the Earth is made up of huge plates or slabs that move around on the semi-solid mantle. Where the plates rub together, fault lines occur. That's what we call them, fault lines. So the Earth has this mantle that's semi-solid. It's not liquid, but it's not solid either. It's semi-solid. It kind of slowly moves. And floating on top of it like a raft on top of the ocean are the plates of the Earth. And these plates float on top of this mantle, and they can actually move. And we call that continental drift. But most people have the wrong idea when they think of this. They think here's the continent like North America, and here's Asia, and those are floating around. And in between is, I don't know, they don't think about it. But the oceans are a plate too. The ocean plates are made of a substance called basalt, which is heavy and sits down in the water. It's like a raft that's heavier, and that raft sits down in the water. But the basalt plates of the ocean sit down in the magma a little bit. The continental plates are made of a lighter substance called granite, and that sits up a little bit. Granite is actually lighter than basalt. And I know if you have granite countertops, you're thinking granite's not light, granite's heavy. Granite's actually light compared to basalt, which is heavier. So think about it. You have a basalt plate that's sitting down. You have a granite plate that's sitting up. If the rain comes down, where's the water going to pool? On the up plate or over the down plate? Over the plate that's sitting down. So the water pools on top of it, and that's your oceans. Do you see? And so the reason why we have oceans is because they're sitting on top. The ocean sits on top of a plate that sits further down than the continents. Does that make sense? And so here's a look at all the plates and what they look like. And here we sit on the North American plate, which is a plate, this entire plate, you can see it outlined right here in blue. This entire plate that we're on actually has both basalt right here and granite right here. And so the granite sits up higher, that's the land. The basalt sits down lower. So our plate has both granite and basalt on it. And this whole plate moves, and it moves in the direction the arrows are pointing. It's kind of curving like this. It's kind of moving like this, if you follow those arrows. Here's another plate, the Pacific plate, and it's moving pretty fast in the direction these arrows are showing. Here's a little plate right here, the Caribbean plate. I don't know how it's moving. The Cocos plate is moving that way. The Nazca plate is moving that way. The South American plate is moving this way. This is an interesting thing going on. Let's look at the Nazca plate and the South American plate. The Nazca plate's moving this way. The South American plate's moving that way. And where this line is, the two plates collide. Imagine two giant plates on the Earth colliding. You think that would wreak any havoc? what happens is this Nazca plate, as it collides with the South American plate, the Nazca plate is heavier. It's made of basalt. So imagine these two plates hitting one another. Let me do it how y'all are sitting. The Nazca plate hits the South American plate and goes under it. And the South American plate gets pushed up over it. And where those two things are hitting one another, and one's going under and one's going over, well, watch my fingers. Whoop. What do you have right there? Mountains. Huge mountains that run all the way up and down the South American coastline.
So can you just be like standing there and it'll just like...
Yeah, but it goes so slowly. It moves about that far a year.
Oh.
So to push up a mountain that's 5 miles high, it might take 5 million years. And so you're not like watching it go. But every once in a while you can feel the movement of those plates, because what they do is they build up pressure, and then they slip. And build up pressure, and then slip again. So they move in a series of slips. And each slip is called a earthquake. Whoa! The ground just moved, man! I know, dude. That was crazy. That's what people say during earthquake. I guess. It's California, right? They have a lot of earthquakes. And you can see everywhere where there's a red dot, that's where an earthquake is. They're all around these plates. We don't have, there's not many in the middle of a plate. They're usually on the edge where the plates are hitting one another. There's actually a line that goes right here through Africa. I don't know why they didn't draw it. There's a plate here where there's a separation. So they call this area here. Also, what you'll get when one plate dives under another one, it'll dive into the interior of the earth where it's real hot, and it'll melt the plate. So this basalt plate dives down. I'm sorry, it should go this way according to how you're sitting. This plate dives down under the Nazca plate dives down under the South American plate, and then it melts down here. And some of the stuff melts and sinks, but some of the stuff is lighter. The granite is lighter, and it melts and it floats back up. And the lava, as it floats back up, comes up and out, and that's a volcano. So there's all kinds of volcanoes. Whoops. There's all kinds of volcanoes everywhere where you see red dots, or these lines. There's volcanoes all around here spewing out lava. There's earthquakes and volcanoes. They go together. And so they call this whole area here where there's all kinds of volcanoes around the Pacific Ocean, they call that the Ring of Fire. The Ring of Fire surrounds the Pacific Plate. Plate tectonics are so cool. It explains everything about geology. It explains why volcanoes are there. It explains why earthquakes exist. It explains why mountain ranges are there. Why do mountains exist in long lines called a mountain range? That's because that was where two plates were colliding. You know the mountain range that runs along the what's this mountain range called here in North America? Do y'all know?
Appalachians.
The Appalachians. The Appalachian Mountains are an ancient mountain range that was formed by an ancient collision of plates billions of years ago. The plates have since then fused, and the separation between the plates is gone, but the mountain range is still there. So the Appalachians are billions of years old. And in those billions of years, they've eroded down. They aren't nearly as tall as they used to be. So that's why the Appalachians are more like hills compared to the Rockies, where the plates are actually hitting one another. Isn't that interesting? All of geology makes sense after plate tectonics. And it wasn't discovered until 1920. A guy named Alfred Wegener said, I think the continents move on plates. That's what the evidence is showing me. And everybody laughed at him, made fun at him, and said, no way, continents can't move. And he was right. So if you're interested in that kind of thing, take a geology class. We don't offer it here in high school. Most high schools don't. which is a crime, by the way. It's a crime. Everybody should know geology. Look at this mountain. See the way the rock is curved right there? It's because this rock has been pushed up by tectonic forces. The rock, those lines of sediments should be straight, but this side has been pushed up by something pushing on the end of it. What could push rock and curve it like that? What is so strong that it can do that? A whole plate pushing against it will actually bend the rock. Isn't that amazing? The Himalayas are the biggest mountains in the world, and they're right here where this plate, this Indian plate, is pushing up on the Eurasian plate and forms these huge mountains here. And they're moving really fast, and it forms the biggest mountains in the world. Anyone here ever climb Mount Everest? Yeah? Oh, really? He's lying. A lot of people die trying to climb Mount Everest. This is a pretty serious climb. If you ever do that, you've done something. Here is the San Andreas Fault. Have you ever heard of that? That's where the North American plate and the Pacific plate are sliding past one another. They're kind of both moving in the same direction, but the Pacific plate is moving faster than the North American plate, so the Pacific plate outraces it. So you got kind of sliding going on there. And you can actually see the line there. This looks like a big crack in the earth.
Could you fall down there?
You could, yeah. That's a big hole that goes down, but it doesn't go that far down. I mean, it doesn't like go down to the middle of the earth or anything. But there is a crack there that you could fall in.
How far down would you fall?
I don't know. I've never seen it. I'm guessing anywhere from 50 feet to a few hundred feet. And then it just kind of comes together at the bottom where sediment has fallen in and filled it up. And so you see, they show here a picture of the Earth diving down below, and of this plate. There's a plate diving down, and this plate goes up. And this, you also, whenever you have a plate diving under another plate, you get a real deep spot called an ocean trench. Have you ever heard of any of the ocean trenches? If you take marine biology, we talk about this stuff. These trenches get down real deep. That can be like 8 miles deep, 6 miles deep. The real deep trenches. I think 6.5 miles is the deepest trench. There are also places where two plates are coming apart in the ocean. Let me show you that. See right here? This area here, the North American plate is going that way, and the Eurasian plate is kind of going this way. And so those plates are coming apart. So lava comes boiling up from the interior of the Earth where the plates are coming apart. And you end up with a ridge of mountains under the ocean going all the way through here. There's all the way, this is called the Mid-Atlantic Ridge, and it goes all the way down, and it's where, like, see this plate's going that way, and this plate's going that way, so the ground just opens up there. This is under the ocean, though, and the lava comes up and makes mountains. So there's a whole line of mountains under the ocean. There's another line of them here, and here, and you can see they're all over the place, these mid-ocean ridges. It's actually the largest feature on the planet is a line of mountains under the ocean that runs all the way around the whole planet. And there's some places where the mountains are so big they stick up out of the water, and that's what Iceland is. Iceland, right there, is where the mountains come up. There's been so much lava comes up from when these plates split that it sticks above the surface of the water. And so there's a little volcanic island called Iceland there. And it's usually cold there, but there's also volcanoes on it blowing up. Interesting stuff.
Are the mountains the same size as like the normal like Rocky Mountain? Like are they the same large mountain size or?
Yeah, they're
smaller?
big. Yeah, if you go to Iceland, they're big. I don't know if they're as big as the Rockies. I've never been there, but I hear it's beautiful. I mean, they have glaciers, they have volcanoes, you can actually see lava. They've got it all. If you're a geologist, you go to Iceland. What is this? No, we don't know. So here's how they know that the continents have moved over the millions of years. And this is, all the continents used to be together in one place. We called it Pangaea. And then the continents over the last 300 million years have spread out to what they are today. And so the world is a changing place. I think this is a video showing that. It doesn't have any audio, but you can see this is computer simulation showing you what the continents have done over time. This is all from scientific evidence. They can trace back in time what it used to look like.
Does this go into the future?
Yeah, it does go into the future. So there's present day, and now it's going to show you what the future will look like.
California to break on or something?
Here's the future.
That's that big flash.
Yeah.
Somebody's taking a picture. This is from some museum.
Wait, so it's going to join back together?
Yeah. Look at this.
Pangaea is back.
Yay.
It's going to all come back together in about 1 billion years. Huh?
What did the sun do?
Then there'll be some moon.
Say that, Carson? I couldn't hear you.
Is the sun gonna be hot still? And
Yes.
is it gonna go out eventually then?
It will eventually. But they figure that the continents come apart and go back together about every 1 billion years. And so it's probably happened about 4 times in the history of the Earth, 4 or 5 times. And one of those times was what formed the Appalachians. And it'll just keep doing that. And the sun is supposed to be like the way it is for another 5 billion years. So it'll probably happen 5 more times before the sun finally expands, and engulfs the Earth and then goes off. And we'll talk about the death of the sun later. So 5.5 is all about the surface of the Earth and these plate tectonics. What about the surface of the moon? What's it look like? Well, the moon's very different from the Earth. It's so small, it's lost all of its heat, or almost all of its heat. So it's not hot on the inside anymore. So it doesn't have magma that moves and causes the plates to move around on the magma. It doesn't have that. So it's kind of a cold, dead area with no plate tectonics. No wind, no rain, no volcanic activity, no atmosphere. Very little water, although there is some, not much. The water is in ice. And it's down deep in some of the craters that are so deep the sun can never shine on the ice. If the sun ever hit the ice, it would melt and then evaporate and be lost from the moon forever. But there's some craters on the moon that are so deep and filled with ice, the sunlight never gets to them. There are features on the moon called maria, large dark areas where lava spread out early in the moon's formation. Maria means sea in, I don't know, some language, Spanish maybe?
No,
Latin?
Mars.
Mar and Mare in Latin is like lake or ocean.
Oh, yeah, that's it. So Maria, they thought they were big lakes, but they're not. And so on the moon you have dark areas called maria and lighter colored areas called lunar highlands. The lunar highlands are old and the maria are younger. How do we know what they're made of? We've flown rockets to the moon, landed people on the moon, taken samples, brought the samples back, and studied them. You may have heard of it. That was the moon landing.
Oh, yeah.
But here are the dark areas. These are the mare. And here are the white areas. These are the highlands. This is the near side of the moon. The far side looks a lot different than from the near side. And so why are there these mare? And by the way, if you look at the moon at night, it kind of looks like it has a face. It looks like it has two eyes and a nose and a half-smiling mouth, a mouth off to the side. They call that the man in the moon. Have you ever heard that? It's not really a face. It just sort of looks like one if you stretch your imagination. Anyway, what happened was early in the moon's formation, when it first formed about 4.5 billion years ago, the moon was hit by some really large objects that created huge craters. That whole thing right there is a huge crater. And so is that, and so is that, so is that, so is that. Big things were hitting the moon early in the moon's life. And it created big dents. And the moon was still hot back then. So imagine something big hitting the moon like my fist. Bam! If I hit it hard enough, I'd put a dent in the globe. I don't want to do this. Mess up my globe. But you can imagine I hit it hard, there's a dent in it. If the middle was liquid, was full of lava, the lava would fill in the dent. It would come up through the cracks I made when I hit it and fill in the dent. Just like water, just like if you dig a deep hole in the ground, water will fill in the hole. Do y'all see what I'm saying? So lava fills in the dents, and the lava is nice and smooth, and it's dark. And that's what the mare are. So the mare are dark areas where lava filled in the dents. And then the moon eventually cooled so much where the lava all hardened into rock. And so nowadays, if you made a big dent, it wouldn't fill in with lava. This all happened early in the moon's history. So that, you can see there's a little crater inside that mare. Actually, that's a giant crater, but it looks little compared to some of these other craters. That crater obviously happened after the mare formed, because it's on top of the mare. So some of these craters, the cratering happens after the mare formed. You look at all the craters on the moon's surface. See, they don't erode. Whenever something hits the moon, the crater never erodes. It stays there for the rest of eternity because there's no erosion happening on the moon. There's no weather. There's no water to fill in and flatten out the surfaces. This is what the Earth would look like if there was no atmosphere and if it were cold. So it didn't have any lava or anything to fill in the cracks. So there's a whole science in counting the number of craters to determine age. The more cratering there is, the older it is. So this area, look at all the craters covering this highland. The highland is real old. Look at how there are much fewer craters in the mare. The mare is much younger. And this mare seems to have the least craters of all, so that's probably the youngest mare. This one seems to have a few more to me, and that one right there has a lot more craters. So that one's probably older. And so scientists can count the number of craters to determine the age of the impact event. The age of the area. What if that was your job, counting craters? Would you enjoy that? About as much as you're enjoying this class? Here's some videos of people walking on the moon. Oh, it's kind of grainy. A little bit. Pretty light, isn't it? I apologize for that.
Maybe it never even happened.
We'll have to remove that. Oh, here we go. Spacecraft descending to the moon.
The simulation is a real thing.
This is real pictures. Way sped up. It didn't really happen this fast. A full rotation of the moon.
Okay.
Of course, the moon doesn't rotate though like the Earth does it. They had to fly something around the moon to get all those pictures. But look at, that's the front side of that's the side we see. Look at all the mare. That's the other side of the moon. No mare. Hardly any. Just one there on the top left corner. Why do you think that is? I've given you the tools to figure it out. Why does the far side have no mare and the near side have a lot?
Because the near side is closer to the moon. There's more.
Yeah,
The stuff that came in to fill the craters is heavier on that side, so the heavier side is going to face Earth. Yeah.
Good guess, but that's not right. But I see how you're thinking, which is good. Anyone else? Y'all can't think of this? I have had students figure this out before.
An asteroid would come into Earth's orbit and go around it.
No, that's another good guess. But actually, the moon is so far from the Earth that the gravity doesn't work that way. It has something to do with the crust.
It's thicker on the other side.
Say it, Leah?
It's thicker.
So what?
So the core, like, when it like makes impact with the moon, it doesn't necessarily reach like the portion of.
That's it. You got it. Give Leah a big round of applause. She figured it out. See, the core is pulled toward the Earth. Here's the Earth. The core is pulled toward the Earth, right? So the crust on this side is real thick, remember? And so the crust is so thick, if you dent this side, the dent might not be deep enough to reach the liquid part. On this side, if you dent it, the crust is real thin, and so you can reach the liquid part. That's it. That's the reason. And so, scientists, when we flew around the moon, we were expecting the other side of the moon to look just like this side of the moon. And they finally flew the first spacecraft to the other side in the late 60s, and they saw it was totally different. And they were like, whoa, why is that? There should be mare, and there's not. And they asked one another, and then they finally figured it out. Isn't that neat? So there's what the far side of the moon looks like. Hardly any mare. Still a lot of craters. But the mare didn't get to form. So the next 5.6 talks about all the craters on the moon's surface and how a crater happens. And you saw some of that in the video about the dinosaurs. The crater, the meteor hits, and there's an explosion, and it throws out a bunch of debris, and you're left with a crater and a rim, and what we call an ejecta blanket with pieces all over and all around. And sometimes it fills in with lava. And there's craters everywhere on the moon. going to talk more about that tomorrow, but read 5.5 and 5.6 tonight. Craters are real interesting.
Do you want me to stop it?
Yeah.